All right, everyone. If you're new in this room, I'll be hosting. My name is Danica. And just a couple notes of housekeeping before we get started. First of all, download the conference app if you haven't done that yet. Build an agenda on there so you know where you're going. And more importantly, rate the sessions. All right, I've been telling everybody it's so important for us, especially this year for the first in-person Iceberg Summit, that we get your feedback on the sessions. So if you could please help us out there by rating all the sessions so we know how we can improve next year. You know, it really is helpful for us. Please also save your questions for the end. We will be passing around a microphone so that we can actually hear your questions. So please save that for the end. And with that, I'd like to welcome Anton to the stage to talk about deletion vectors. Thank you.
Hi, folks. It's a pleasure to be here today. I began working in Iceberg in 2018, and it's incredible to see how the project evolved since then. None of this would be possible without the Iceberg community, and it's truly a privilege to be a part of it. So today we'll talk about deletion vectors. By the end of the presentation, you will understand why the community cares so much about row-level operations, existing delete mechanisms in V2, and everything about deletion vectors in V3. So what's the motivation for adding them, design choices that we made, and what that actually means for engines and users that work with Iceberg. The need to modify particular records in tables with petabytes of data is not new. It predates Iceberg in other open table formats. Data engineers always had to remove records for regulatory compliance. They had to correct issues that happened during ingestion, and also to populate changes to fact tables. The problem, however, is the early big data landscape was lacking tools to handle these use cases efficiently. As a consequence, data engineers frequently created pipelines where they would query partitions of the table that were affected, join them with incoming changes, perform complicated transformations, and then write the new state back to the table, overriding original data. This worked. It was very popular, but it had a lot of issues. It was unnecessarily complicated, it was error-prone, inefficient, and frequently led to corruption of the table. The underlying problem is the inability of the table format to natively represent row-level changes. Therefore, it was critical for Iceberg to provide multiple built-in materialization strategies for various use cases. Users can eagerly replace entire data files, which is known as copy and write, or mark particular records as logically removed, which is known as merge and read. Deletes in merge and read can be done either by position or by equality. All of these three options can actually be used within the same transaction, providing the ultimate flexibility to engines. Today, we'll be focusing only on position deletes in merge and read. Copy and write and equality deletes remain unchanged in V3, though there are talks about what we want to do as equality deletes in the future, but it's out of the scope for now. Let's take a look what Iceberg did for position deletes in V2. The V2 version of the spec relies on position delete files that identify rows to be removed by file location and row position. Those are regular Parquet or Avro files with two columns in them, file path and position. They may have different granularity. Initially, Iceberg persisted all of the deletes for a particular partition into a single file, and then it migrated to persisting deletes for a given data file separately. So here's an example of partition scope deletes. Suppose you have two data files in a partition, and you need to remove rows from both of them. Under partition granularity, you can put all of your deletes into a single file. Under file scope, you actually have to separate them. So you end up producing a delete file for each affected data file in each transaction. The transition from partition to file scope allowed Iceberg to fix a lot of issues during planning and the so-called problem of false positives. Previously, deletes were assigned by partition. So readers ended up opening a lot more unnecessary files that didn't have any relevant deletes for them, and that was creating overhead. This problem does not exist with file scope deletes because Iceberg has enough metadata to know where that file applies to at planning time. The beauty of position deletes is that you have fully vectorized reads. So you read your data normal, and then you load all of the deletes into a bitmap. Iceberg uses roaring bitmaps for that. The bitmap itself hides particular records from the engine, essentially marking them as removed. Writers also revolve around roaring bitmaps that are used to buffer incoming changes. Once the task is done, the state is then flushed into a Parquet file, for instance. While the V2 design worked fairly well and was deployed in tables with tens of petabytes of data, it did have issues. So first of all, users had to pick between fewer files on disk with partition scope or targeted deletes without false positives with file scope. Ideally, you wouldn't have to make this trade-off and make this choice. You would have both. The second problem was different in-memory and on-disk representations. So both on reads and writes, you had roaring bitmaps, but on disk, you had Parquet data. And every time you read the table, every time you wrote to it, you had to do this conversion. It wasn't crazy expensive, but it was unnecessary, and this just was the complexity that was not needed. And finally, the spec was very flexible. It allowed stacking an infinite number of deletes against a data file and did not require engines to do any compaction. That created problems because none of the engines did any maintenance until the tables became unqueryable, unless, of course, the users maintain the tables themselves. So V3 was an ability for us to reconsider the design of position deletes. The V3 version of this spec adds the notion of a deletion vector, which was inspired by Delta Lake. The DV marks a record as removed by a position in a bitmap. So Iceberg was already using roaring bitmaps during reads and writes, but V3 takes it a step forward. It is now possible to persist those bitmaps directly as binary blobs in Puffin files. We also changed in the specs so that there can be at most one deletion vector per data file in a snapshot, which essentially requires engines to do maintenance during write. So you no longer have this read degradation, and the performance stays good, and it's an engine responsibility to perform that. Here's the blob layout. It has multiple sections in it. The first one is the length. The length is the number of bytes occupied by magic bytes in the bitmap itself. Magic bytes exist there as a sanity check. So essentially, once you jump to this offset, you want to make sure that what you're about to read matches your expectation. And then you have the roaring bitmap itself. It's persisted using the portable format. This is as close as you can get to a standard for 64-bit roaring bitmaps. And then at the end, you have a 4-byte checksum. The checksum is there for data integrity. So basically, if for whatever reason you cannot deserialize back your bitmap, you would like to understand whether that's a faulty storage that gives you bit flips, or there was a problem with the way you serialized the bitmap in the first place. So overall, 4 sections, and this is what we call by DV blob. DV blobs are persisted in Puffin files. They can be many blobs in one Puffin file. Puffin files were added to Iceberg to persist table statistics. The primary benefit of a Puffin format is in the ability to persist and retrieve a binary blob efficiently. It's not possible with Avro or with Parquet. Um, the puffin files are fully self-descriptive. They have a footer. For the deletion vector puffin files, you have the offset, the lengths, the reference data file, and the cardinality of each deletion vector in the footer. So if you get access to a puffin file, you would be able to make sense of its content even though you don't have the metadata around it. It's extremely helpful for debugging purposes, and just helps make sense of it. However, it's not being used during reads because of how the metadata captures DVs. Each DV in the metadata is tracked separately, even though they are persisted in the same puffin file. So at this example, we have a puffin file with 2 DV blobs in it. Each blob becomes a separate metadata entry in the manifest. Each entry has content type as position deletes, file format as puffin, the file path is the same as well, but we have 3 more fields that kind of distinguish them. First, you have content offset, then content size, and finally the reference data file. The offset is basically where you need to jump in that puffin file to start consuming your blob. Content size is the number of bytes you have to read to fully consume the blob. And the reference data file is to which data file this blob belongs to. All of these 3 are new in V3 and basically allows us to track each blob separately while persisting them in the same file. So this is a key design decision that basically allows us to not have tiny files on disk, yet still have targeted deletes. And the important part that the blobs can actually belong to different partitions. So previously, if you worked with V2 Iceberg, if a transaction modified 1 million partitions, you would have to create at least 1 million tiny delete files. This is no longer the case because puffin files can contain DVs for different partitions, so you can coalesce them across partitions. And that is the key design principle that kind of removes that trade-off of partition versus file scope in V3. Right, to summarize the benefits, you have targeted deletes without tiny files on disk. You have faster reads and writes because there's no conversion between bitmap and Parquet data. And engines actually are required to maintain these DVs in place. So if an engine adds new deletes to a file, it actually has to combine that previous blob with the new one that is encouraged to be done in distributed fashion and then commits it in the transaction. So the benefit of that is that the read performance does not degrade as quickly. To kind of put this all into perspective, let's take a look at an example. So suppose we have a table. The table has 3 different columns. ID, salary, and department. It's partitioned by department, and we're creating it with the format version 2. Let's assume there is some data in that table. We have 2 partitions. There are 2 data files in each of those partitions. We have data A and B in one partition, and then data C and D in another one. Now, if there is a delete that comes in that modifies some records in all of the data files, right? Then this is how it would be represented right now with V2. For each data file, you would have a new delete file. So for data file A, we would have a deletes A file, which is basically also using Parquet. And that would be for each affected file, you would have a new delete file. Now, let's say there is another delete that comes our way. This time, we modify records in data file A, B, and D. So there are no changes for the data file C, right? Only 3 of the 4 are modified. In Iceberg 1.8, we added support for synchronous maintenance even in V2 table. So what would happen if you're working with Spark is that Spark would combine the previous deletes with the new ones and replace them in the new snapshot. So basically, for the files that are modified again in this transaction, you will have new delete files as well. So in this case, we have another delete file for data A, B, and D. The C still remains the same, and Iceberg would actually remove the previous delete files from the table state. So the next time you read this table, you only have to apply the new version of the deletes. What was important for us is the way how you can, there are a lot of V2 tables that are using position deletes. So it was critical to create this seamless transition to V3, and therefore the previous V2 deletes are valid in V3, but you cannot write them anymore. So if you're migrating a table, it does not require rewriting deletes, rewriting data. You can just bump the version, and the next time the write would happen, this is where the conversion would happen. So in this case, we're basically upgrading this table to V3, and then the next delete statement that also modify records for data A, B, and D would have to produce DVs, right? But the important part is that once the first write to the V3 table happens, we can produce just one puffin file. That one puffin file would contain 3 different blobs for file A, B, and D, because these are the files that were affected by this transaction. And once the blob and the DV is added, the previous deletes no longer apply. So the first time you add a DV, it has to include all the previous historic deletes that existed in that table. And the important part is that because the file C was not modified, the previous V2 delete is still valid and still remains part of the table. So basically, whenever you read the table, you would apply the DVs for file A, B, and D, and you'd still have to apply the previous one for file C that was there before the table was upgraded. And this is basically like if you have one more change, right, where you delete this time records from data file A and C, then what would happen, you actually don't have to rewrite the entire puffin file that you created before. It just naturally happens that some of those DVs will no longer be part of the table state. So in this case, the new transaction would produce a new puffin file for blobs A and C, and those would be valid. But the blob for file A that existed in the previous puffin file will no longer be referenced by the current version of the metadata. So essentially, you don't have to rewrite those larger puffin files each time you modify the table. You just continue appending them, and then the previous DV would fall from the current metadata and then would eventually be expired. So that's the gist. I wanted to keep it short to see if there are any questions, because usually like there are questions about why we did it, what that means. I tried to clarify that with the example, but I purposely left more time for questions so that we can discuss this if needed. Thank you. Sure. That's a good question. So the question was about the number of blobs that, how to decide how many blobs to put in a single puffin file, and what's the story there. I would say that naturally when you do the write, all of the blobs that are being created from a single task. So if you have a distributed write and then you have a single task in one node, all of the DVs that are produced by that task would be written to a single puffin file. So kind of the number of puffin files would correlate with the parallelism of your job initially, right? So you're no longer, the big shift here is that previously each task would create a number of delete files. So for each partition that that task modified, at least that, now is just one file. So that's the improvement. And then the compaction we recommend, I think the default is 2 GB per puffin file. So basically you can stuff 2 GB of blobs into a single file, and that's what we consider as a reasonable limit, what we recommend. The only performance disadvantage would be from the storage perspective. So what we've seen is like S3 throttling was the previous design. So it's more like you reduce pressure on the storage rather than it's an issue that would like, it doesn't change much on the Iceberg side, more like the storage. Because like if you're working with a table that contains 20 million data files, right? You don't want to have extra 20 million delete files on disk that kind of overwhelms the storage. So that's the only performance difference that you would see.
Thanks. I have two questions. One is, what's the reading overheads of the puffin files comparing to the previous, like the Parquet-based delete change log?
Yeah, that's a good question. So previously, like the reading performance depended on whether you used partition scope, Parquet files, or file scope files. It was partition scope files. Basically, you had all the overhead of reading a Parquet file, like you read the footer, you decode, decompress, whatever. And then you actually had to go record by record, and unless you could filter row groups or pages, but usually you would go record by record, and you would find among the records for that partition whatever applies to a particular data file. So you'd have to scan and then find whatever matches the data file that you're currently reading, and then you would take those records and then you would create a bitmap out of them, right? The bitmap of positions. With file scope deletes, it was slightly more efficient because we knew that the entire, like all of the records applied to that file, so we didn't have to do that filtering, but you still had the overhead of reading the footer separately, multiple requests, and then decompression of Parquet data, dictionary encoded. Usually that was the case because the files were dictionary encoded, whatever. And then you would have the overhead of creating the bitmap out of that. In the new design, it's a single request. You know the offset where you have to jump in the metadata. So you just jump there and then you do a range scan for the bytes, which is extremely efficient. And this is the only request that you do to the storage. And that's already the serialized bitmap. So out of that, you just deserialize the bitmap. You don't have to reconstruct it because the reconstruction was more or less expensive. Because once you start with an empty bitmap and then you flow the positions into it. And the bitmap would adjust because like the roaring bitmap, the beauty of it is that it has multiple sections. And once you add data to it, it will adapt which model it would pick for a particular section, whether it would use a bitmap, whether it use an array of positions and whatever. So you kind of get rid of all of that. It's just extremely cheap in the new design. I think we have some benchmarks, I just don't remember the numbers, but it was just nothing. It was just that fast. So basically the only overhead is a single read to S3.
Okay, I have another question. Like you mentioned the version upgrade right now, the default implementation is almost a lazy upgrade.
Mm-hmm.
You will only change to puffin files when like upcoming changes happens. Is there a way to trigger that upgrade like proactively?
For sure. You have all the utilities, so technically I think Edward did maybe it's not fully shipped yet, but there would be an action that where you can proactively do the conversion if you want that. But it was important to keep the migration simple so that it's zero rewrite. If you're encouraged to do that, but it's not a requirement. Yeah, so Amok did a lot of that work, and Spark and Edward also did a lot of the maintenance stuff of the things. So there should be enough utilities to kind of deploy DVs in production.
Yeah, in this example, you mentioned that when a new delete happens for the A Parquet file, it gets unlinked in the manifest file to point to the EBD puffin file. So I can imagine, like, if you have like 2 gigabytes of puffin files, there can be, like, if you're running a lot of these delete operations, then many of the deletion vector blobs in the puffin file can no longer be pointed from any of the any of the manifest file entries. So is there some procedure like to clean up and gather all the deletion vectors that are actively pointed by some snapshot and create a new puffin file out of the existing puffin file?
Yeah, exactly. So you captured it correctly. So naturally, like most of the DVs would fall off the scope, and they would be just expired through the normal. So this basically the first puffin file would be cleaned up as long as the DV for B and D move away out of the scope of the current snapshot. But let's say there is a use case where you have hundreds of DVs in a single file and 99 of them are out of scope, but there's one that still prevents you from expiring that entire blob file. So for that, we would, I don't think it's implemented yet, but Edward's working on that utility where it would actually take all the live DVs and put them into a new puffin so that the previous delete file kind of falls back completely and out of scope, and then can be cleaned up through just a normal expire snapshots procedure. So it's nothing extra in terms of maintenance that the user has to do. It should be automatic.
Next question over here. Did you guys try to measure your performance gain with DV? So I mean, read performance, any benchmark? So of course it's dependent on the workload, but it's rather 5% or 5x.
Well, it depends how you measure it. There were like a lot of benchmarks that are part of the PR. So if you're interested in that, like part of the proposal, the design doc actually included a section. I don't remember the numbers, but it was something ridiculous because the cost of reading a DV back was like a millisecond, couple of milliseconds, whatever, and it was like in percentage, it was like hundreds of percent, so it was like dramatic difference. In absolute numbers, that depends, right? So it's still, it was still mostly happening concurrently, and it's really hard to measure it because you can bend the numbers you want in the way you want, and like you can stack up just enormous amount of deletes as well. And so the difference in terms of like percentage was dramatic. It was just very efficient. And all of that is part of the design proposal. I just don't have the numbers with me.
Next question, right over here.
Yeah, so in V3, is this going to be an optional feature that you enable and you'll continue supporting the previous way, or this is going to be the default and you deprecate the existing mechanism?
It's deprecated, it's enforced. You cannot add the old style position deletes anymore to a V3 table, but whatever you had already is still valid. So readers in V3 have to support the previous deletes. So that's how we support the zero copy migration. But no, you cannot add the previous position delete style anymore after you did the upgrade.
So in that case, where are we in terms of support for deletion vectors in Spark and Trino, Flink?
Iceberg 1.8 came with support for DVs end-to-end in Spark 3.4 and 3.5. It will be in 4.0 as well, so it's already there. I know there was a PR in Trino to add support for that, so we see the community is moving really fast, and I anticipate our friends at Snowflake, I heard some, maybe like we can ask Russell and others, but I heard that they're working on that as well. So I do imagine this being really quickly adopted. And the reason why it's quickly adopted, because most of the engines already used roaring bitmaps in memory for reads and writes. So it's just, they can simplify the implementation and kind of throw away some of the code and should work. That's what we did in Spark. So the migration in Spark was fairly simple. We just had to modify some implementation the way you kind of build the bitmap, but the rest was still the same.
Next question over here.
Sure.
Yeah, and then, so I have a similar question about the performance as well. So most of the workloads that my team uses is basically copy and write to avoid the read penalty in the current spec. So does this enhancement take the performance closer to copy and write to an extent, or do you still recommend copy and write as the preferred one and merge and read on very special use cases?
Based on the experience, I think if you use copy and write and it works for you, it's a good option. It's by no means a faulty design, and it's still the preferable option if you have a targeted operation. So if you have a table, but you know you're going to be affecting a small portion of it, I would argue that copy and write is still a good option. Or if you're working with some bulk changes, maybe you accumulated all of the changes for a day and then doing one job to kind of populate all of those changes. I think that's still a good use case for copy and write. Merge and read in practice was used wherever the copy and write failed. We had a lot of use cases where you had deletes that were scattered across the entire data set. So imagine like removing a couple of records from every data file. Yeah. With copy and write, that would be rewrite of the entire data set on each batch of changes. That was not sustainable. Some of our tables were like tens of petabytes, so you couldn't do that at all. So there, the position deletes and DVs, that would be a saver, right? So we had to use them in those use cases. And the overhead of applying a DV, as long as you're like stay within the reasonable threshold of like covering at most like 20% of the records in a file, is negligible. It's really about a couple of percent. Usually it's within the error, like you wouldn't really notice there was a DV. All right, especially with the new design, because just one DV. It's not like with V2 where you had to merge the delete files first. That was the expensive part, right? Here it's different. You do a little bit more work up front during writes, but then your reads are really efficient. So as long as you stay within that 20% of deleted records, I think you should be good.
Thank you.
Do we have any other questions?
I know in the Iceberg V2 spec, or just I think before that even, when we do maintenance and compaction, we usually pass in something like a delete file threshold to actually, compact those delete files and data files, right? So do the delete vectors now kind of render that obsolete, because now we're really only working with like a single file every snapshot, right?
There are still thresholds. It's just we think about them differently, because there's always, so the previous threshold was on the number of delete files that applied. So like if you had 10, or I think it was 5 by default, whatever, then you would compact them. Now we're thinking about them differently, because there's always just one, but we look at the cardinality of the DV. So if the cardinality of the DV removes more than 20% of the records in the data file, we would compact them. And there is no need to do the minor compaction. So because just one DV, so you don't have to kind of combine DVs. It's about when you merge the DV into the data file, and that's where the cardinality is important.
Got it. So now it's like a cardinality thing within the single file rather than the actual number of files as it pertains to a data file.
Yeah,
gotcha.
And it should be, I think Edward merged that already, so it should be part. I'm not sure if it's configurable at this point, but should make it.
Yeah. Cool, thanks.
We have time for a few more questions. Anybody else? Yep. There you go. Oh, thank you. In the back here.
Hi, everyone. Hi, Anton. I work with Anton. He's used to me asking questions. I come from the Delta community, And I would love to know about the decision behind making the puffin file and putting multiple DVs into a single file like that, which, if my understanding is correct, is different from what Delta decided to do.
The difference here is that we do use puffin because of the footer. So the decision to go with puffin was the debuggability. So it is frequent to just have access to random files. So like suppose something happens and something goes wrong, and you look at the metadata tree and you can find the particular DV file, but it exists in the file system. So you're trying to understand, okay, what's going on? Like where that puffin file belongs to, right? And this is where the footer is important, because you can go to that file that may not be part of the table state, so you don't have any metadata in the table for it, but you can go to its footer and you still know how to read it, which data file you reference, and what's the cardinality. So you'll also know when that file was created, so you can somehow debug and reconstruct what went wrong. I think the Delta protocol still kind of puts multiple DVs into the same file. It just doesn't have the footer, and because Delta doesn't work with puffin. So I think that's the only difference. Other than that, it should be exactly the same.
Any other questions? Oh, many more questions.
So the naming scheme that you got there with the partition names in the file name, and I think puffin is also used for other purposes, like, right?
Oh, sure.
So wouldn't there be any conflicts, or people might accidentally, chop them off, right?
No, they all part of, so the maintenance is aware of the new design, so it's kind of taken care of. The names of the puffin files themselves are also descriptive, so usually there is a DV prefix, so you can kind of, just by looking at the name of it, you can guess what that is. Same is also applied for whatever puffins used today, which is table stats. Usually the name of those files are also kind of descriptive enough so you can make sense of it, but they are tracked completely different. So the table statistics, which was another purpose of puffin files, is tracked separately. I think it's tracked from the root file, and the DVs, they are tracked from manifests. So the format is aware, and one just accidentally remove them. So it should be taken care of right now.
Okay, thank you.
Another question?
So these DVs only apply to positional deletes, but you mentioned there's some discussion going on for equality deletes as well. Can you say a little bit about that?
Well, yeah, I think it's a sticky point in the community. A lot of people love equality deletes because they're so cheap on write. So especially for the streaming use cases where you upsert to the table, the cost of doing an upsert, whether it's a petabyte of data in the target table or a gigabyte, is the same. You don't touch it. That's the beauty of it. But then, like, you kind of shift the complexity to the reader. So equality deletes extremely fast and write, require aggressive compaction. So that's where we are right now. And I know a lot of people who manage to successfully deploy equality deletes in its current form, but they do aggressive compaction, and that works for them, right? The problem that it's, again, a lot of that is on the users to organize that compaction. So frequently what happens is that equality deletes are being stacked up, and then you can't read the table anymore. And that's the problematic. And I think there are multiple ways that the equality deletes implemented in the industry. Impala does a join, anti-join for that. Spark does per task hash set. So we're talking about, there are two ways we can improve equality deletes. Either we have to prove that you can replace them with position deletes, and that means having some sort of inverted index from data to a position. but then that index has to be probably distributed. You have to incrementally maintain it. Where do you store it? That's one option. The other option is to go for what I think Tabula did early on, and I know it's like a popular pattern where you have a table and a view on top of that table that kind of squashes your data. And then you don't have equality deletes. It's basically a table and a view on top, and then at some point you refresh the table, and then the view becomes like nothing, essentially. So yeah, there are those two options for kind of improving equality disease and deletes, and there's the third option is to maybe provide some utilities for like LSM tree-like structures where you would accumulate those equality deletes in memory and then flush. So these three options that are being discussed, but nobody proved which option we should go for.
Thank you.
We have time for one or two more. Yeah, at the front.
Thank you. And regarding the previous question, sorry for bothering with the equality deletes, but for streaming use cases, basically right now what we are seeing is positional deletes are the pain, because when you have heavy compaction and you have equality deletes, everything works okay unless you introduce positional deletes, and they block compactions completely because it's hard to resolve those commit issues during the compaction.
That should be resolved already. That was one of it was another reasons to migrate away from partition scope to file scope, and even in V2. So as something that should work already out of the box in like latest Iceberg version. So the problem was there that again that false positive assignment, because like the position deletes were assigned by partition. So Iceberg thought that, okay, something like was the Fling job where you have position deletes and equality deletes. Iceberg treated that position delete file as a conflicting because it kind of applied to the entire partition that caused the compaction to fail. Once we migrated to file scope, that should not be the case, because that position delete, first of all, they kind of separate. So for each data file, they would be separate. So Iceberg is aware where it belongs. So technically, there should not be any conflicts during the major compaction. So that should go away already.
Unfortunately, it's not for compaction jobs or for anything that is yet, but yeah.
I'm happy to look into that. It should be addressed. If not, then maybe you can look into this more. But it's definitely possible to kind of fix that.
Sure, thank you.
Who wants to ask the final question? All right, I guess you were the final question. So let's give Anton a round of applause. Thank you so much.
Thank you.